Hi everyone and welcome to today's Physics Daily Booster. This is number 8 in our series for paper 1 and it is one of those advanced information listed topics. Now parts of what we're going to go through today are on both the foundation physics and the higher physics, including one of those packs. So lots packed in that's been listed on the advanced information. First thing we're going to look at is one of the calculations. Now, as we know, we don't have to memorize any of these formulas because we get our formula sheet in the exam. Do remember to use that. What we're going to look at is work. When we start talking about work in physics, we're referring to the transfer of energy. So we use forces to transfer energy between those different stores, and usually it's done against either friction or gravity, depending on the scenario we're looking at. The most likely question to come up here is, of course, a calculation question. And in order to do your work done calculation, it's going to be force times distance. So what do we need to look out for in this? Well, first of all, we need to double check that our distance is in meters. Quite common for them to give you the distance in centimeters. And obviously, in order to convert to meters, just divide by 100. Now, obviously, we can put this into a triangle, rearrange if we need to. But if you are using the triangle to rearrange, do write down your correct formula. So if, for example, we wanted to work out the force, then you can use a triangle to do the rearranging, but then write down force is work done divided by distance, because that means that you are going to get the mark for having the rearranged formula, if that is a mark that's available for that question. Without seeing the marks, given how many marks they're awarding, it's hard to know, but show all working just in case of silly errors in the exam. Second calculation we're coming on to is power, which is the rate of transfer of energy. And again, formula on the formula sheet, but power in watts is the work done divided by time. So what do we need to look out for here? Well, first of all, make sure the time is in seconds. If it's given to you in minutes, convert to seconds first. Secondly, this can come up as two kind of styles of question. Style 1, they're going to give you two little parts, so the part I and the part II, which is where they're going to have part 1, the part I, is going to be calculate work done, and then your part 2, the II bit, that's going to be using your answer to part 1 to calculate power. Now, as we've said before, if you, for some reason, have a complete mental block and can't think how to use a formula on your formula sheet to calculate work done, as long as you write down an actual answer in the part 1 section and you use that answer in your part 2 would be marked correct, even if your part 1 was wrong. So never leave part 1 blank and then leave part 2 blank because you didn't have part 1. Shove any old number in your fancy and then use that in part 2, okay? Obviously, you're not going to get the marks for part 1, but you can still get part 2 marks. Second way they could ask this is literally just to give you a slightly higher mark question where they're just going to ask you to calculate the power, but they're not going to give you work done. You're going to have to work that out yourself, but they're not going to be explicit in telling you that's what you've got to do. So they will give you a force, a distance, and a time, and ask you to calculate power. So obviously you can't do that directly. You've got to calculate work done first, then divide that by the time to get your power. So two-step calculation, show all stages of the working, same thing. Just look for the formula sheet. What do we have that we can use? Do that first, then can you get to your final answer? The next little section we're going to come on to then is all about what happens when we apply forces to things. Now, this has been a question in the past, sometimes multiple choice if my memory serves, which is just asking us how many forces we need to apply to an object in order to cause this change, either stretching, bending or compressing. And the key thing here is it's got to be more than one force, so 2 forces is the general answer they're looking for there. When we consider applying forces to materials, there are 2 terms that we would apply to those materials based on how they react. Plastic materials are ones that do not return to their original shape once we remove the force, and elastic materials do return to their original shape when we remove the force. So think about a bit of plasticine for plastic. You can kind of smush it into a weird shape, remove the force, it stays in whatever shape you put it in. Whereas the elastic, something like your rubber band, once you've stretched it, if you then let go, it goes back to its original shape. The practical that is listed on the advanced information is all about how springs or basically elastic materials behave. Now, what we actually find here is this is just looking at something called Hooke's law. Now, Hooke's law itself is an experiment you should have done where you'd had a clamp stand on the desk with the little spring hanging off the clamp itself. You measure the length of the spring at the start and then you add masses to it, measuring the new extension of your spring. So that's the basics of the practical. In terms of safety features for this one, because if it is one of the practicals, safety is one aspect, we should make sure that the clamp stand is clamped onto the desk using a proper G-clamp to stop it toppling onto feet. We should obviously make sure that safety goggles are on in case the spring is going to potentially snap or ping into eyes, etc. And that you should make sure your feet are well clear of underneath the area that you're doing this so that the masses don't fall onto toes. Remember the basic lab safety stuff of stand up, tuck in sort of ties or bags under chairs, etc. None of that gets you marks on safety. It's got to be specific to the experiment. Now, what are we going to use to measure the length? A ruler, okay? What could be potential sources of error in this experiment? Well, first of all, you've got to make sure the spring is steady when you take the measurement, because if it's just gently bouncing, what we're going to find is that could lead to inaccuracies. You've got to get down to eye level to take that measurement, otherwise again, inaccuracies could be there. You need to make sure that the ruler is vertical as well, because if it's on a slight slant, you're going to get a different reading. Now, what we do is once we've actually done the experiment, we've got our results, we're then going to plot a graph of your force, which is the weight in newtons, against extension in centimetres. So, what we have first of all is we will have a point in 0, 0, okay? Because when we apply no force to it, there is no extension. So you will have that origin at 0, 0 on this graph. Then, as we add masses, obviously we'd plot our points. Potential graph question here that we could get. Remember, when plotting a graph, please pick an appropriate scale to fill more than half the graph paper, both vertically and horizontally. Label your axes with both the heading and the units, and plot your points as a nice cross using a sharp pencil, because that means we can see your points after you've drawn any lines of best fit. Now, if we look at the graph in the bottom left corner, this is our typical graph of extension of a spring. What we have initially, so this first section down between 0 and about 1.5-ish is a nice linear section. So we've got a linear relationship. That's because as we add a particular weight onto our spring, the extension will always be the same. So what we find is that at that stage, that first little straight line part of our graph, then this is a linear relationship. And it continues in that linear relationship until we get to this point called the limit of proportionality. And I think on this graph it is roughly here. Okay, so it's basically where your straight line ends. That's the limit of proportionality. As we go beyond the limit of proportionality, what we find is that it doesn't follow that linear relationship anymore. Instead, you can see that the extension has basically started to curve off. It's not just keeping going up in that nice straight line. So what we find here is, as we go beyond that point, we've exceeded the elastic limit of the spring. That means when we actually remove those masses from the spring, it's not going to return to normal. It's been permanently deformed. Below that limit of proportionality, then what we're going to find is, removing the masses, the spring goes back to how it was originally. They can ask you to calculate the force exerted by a spring or the spring constant if they get you to rearrange. Again, on the formula sheet, this one right here, Bits to watch out for, again, is going to be your extension, making sure it's in meters, not in centimeters. If it's in centimeters, convert first of all. And then all you got to do is spring constant times extension, or if they want you to work out the spring constant, just the force divided by extension. So nice and straightforward. If they want you to work this out from the graph, then all you need to do is work out the gradient of that linear section. So just draw your little triangle on the graph and then obviously divide to get the gradient of the line. What we find is there's another calculation, again on the formula sheet here, loads of calculations. This time energy transferred in stretching. So 0.5 times spring constant times the extension squared. Now please be careful here. Lots of people get this little squared bit wrong in one way or another. Option 1 of getting it wrong, forget it altogether. Don't forget it. Second way that we get it wrong is that you don't just square the extension, you square the whole thing. Again, not right. It's only the extension that is squared. Third thing, the extension is given to them in centimeters and they just use that. Got to be in meters, folks. So just make sure that you're not making those common errors here, but the formula on the formula sheet. If we consider the scenario of an elastic band, which is the kind of other experiment that you should have done after the spring, we don't get that same shape graph when we plot our force against extension. It's a non-linear relationship here. So what we find is rather than having that nice straight line at the beginning, we don't get that. Okay, so bear in mind that our springs do have that linear relationship at the start. Something like an elastic band does not, it's non-linear. Now, what we do know is that when materials deform, they store energy. So think about stretching an elastic band. When you've got it held in that stretched position, energy is stored. Obviously, when you release it, the energy is released. Now, scientists have actually started to use this principle to actually design materials that kind of utilize that principle. So we've designed materials that transfer the energy back as they regain their shape. So obviously that's very useful if we want something that returns to its original shape afterwards. Think about some of the new glasses that you can get, which obviously when you sit on them would get bent, but when you then stand up they go back to normal. Brilliant, no new glasses. Other materials are permanently deformed on impact, things like your crash barriers. And that's a very good thing. This last thing you want is for a crash barrier to then restore to its original shape after a crash, because at that point your car is getting flung back across the road and that's not good news for the passengers. Final thing to do for today then to check your understanding is head on over, have a go at the quiz, see how well you've understood it. If there are bits you want to look at in more detail, obviously there's the videos on the main channel, your revision guides, your notes. Look at some past exam papers to get a feel for the kind of questions they ask you here. Don't forget to join us again tomorrow for our next Physics Daily Booster.